Okay, so we're looking at 2.6, limits at infinity. What's the concept here? Well, if we see a function like this, what happens when x becomes large as it goes out, gets really big, 100, 1,000, 1,000,000? Notice that we have x squared both top and bottom. So if we look at a table of big values, now notice these big values on the table says plus or minus. So both positive and negative big values. We can see values of f of x, the function values, the y coordinates, get extremely close to 1, right? And we can see that on the graph too. As x is going out on both the right side and the left side, it's getting close to that red line at 1. So we would say the limit, first of all, the limit as x goes to infinity, that's on the right side, is 1, because that curve, or the blue curve, is getting close to that red line on the right side. And the notation we use is this, L, and L is 1 in this case. And it just says x is large. That's what's happening when x is large. So this is the intuitive definition. And here's another notation, again with arrows. As x approaches infinity, f of x approaches L. But you can see there's 3 ways for a function to approach this red line, which we're going to be calling a horizontal asymptote. So it could approach the horizontal asymptote from below and never quite get there, but always be a little lower. And then it could approach the horizontal asymptote from above. This is like the exponential function. And then it could also, what we call, converge on that line from both sides. Some functions do that, oscillate, and then converge on that line. All right, so going back here, this is kind of just a summary, but what we're seeing here, what they're pointing out here for the first time is it also has a limit as x goes to negative infinity. So that what's happening on the left side is also approaching 1. Okay, so that's just another definition. It can have a limit going to negative infinity. Now, these are not necessarily going to be the same number. All right, so it just points out, like, if you look on the left-hand side of a graph, what's a number doing as it gets way out there? Is it getting closer and closer to some horizontal line? All right, so it says there's a horizontal asymptote if either it gets close as it goes to infinity or negative infinity. Okay? And sometimes it's not the same number. It can approach 2 different numbers if it goes to the right and to the left. Now, here, this is a function we use a lot, this 1 over x. So 1 over x as x goes to infinity goes to 0. And really in both directions, okay? So when x is positive, big positive number, or big negative number, either way, it goes to 0. So I just want you to remember that 1 over x, because that happens a lot. We use that a lot, that 1 over x. So it has, you could say, a horizontal asymptote at 0. This curve, 1 over x, has horizontal asymptote at 0 in both directions, right? It's approaching 0 from above as x becomes large positive, and approaching 0 from below, so above, and approaching 0 from below as x is large negative. And there is also a vertical asymptote, right, at 0, x equals 0, I should say. So the horizontal asymptotes are at y equals 0, and the vertical asymptotes are at x equal. There's only one vertical asymptote at x equals 0. So occasionally we're paying attention to that vertical asymptote as well. And then here's something else. If you have basically x1 over x to any power at all, it says r is a rational number. Well, that can, pretty much every number on the number line that you can think of is a rational number. Fractions, decimals, whole numbers. So that's always going to go to 0 because it's always going to grow, basically, when x gets large, and in both directions. And so when the denominator grows, kind of without limit, without bound, then the whole thing goes to 0. The whole thing gets smaller and smaller. So we use that, and you'll see this very soon, like right here. So this is, I'm just throwing through this example. This is like typical problem from this section, and where you're taking the limit of like something like this, where this is a rational function, as x goes to infinity. And we talked about some limit laws the other day, and we're going to see those in action. But, okay, so what we're saying here is, let me just go back. It says we first divide both the numerator and denominator by the highest power of x that occurs in the denominator. So we look at the denominator, say what's the highest power, and we divide every term, top and bottom, by that highest power. So in this case, x squared. So here we go. So we've divided the numerator and denominator by x squared, and then we've broken it up into separate little fractions and reduced each fraction, like, x over x squared is 1 over x, and so on. And then, so that's just simplifying. But then we're going to use some limit laws, and the limit laws come in right here. And these are limit laws I mentioned the other day, where you can like get the sum or product. The limit of the sum or difference is the difference or the sum of the limits. You can just put a limit in front of each one, and then take the limit. And so here we are taking, remember when I talked about 1 over x is going to be a big deal. And 1 over x to the r, 1 over x to any power, what we just saw just now is all those are going to become 0 as x goes to infinity. So everything I've circled, all those limits are going to become 0. The only thing that's not are the constant functions, 3 and 5. Now, just in general, I know this is kind of tedious, so you may not see me write this step. You may, and it's okay if you want to skip that. We all realize it's there, but basically we're taking the limit, from here to here. If you wanted to skip down, we are taking the limit by plugging in you could say plugging in infinity. and just to go backwards, this also, if we wanted to skip a step, I guess we could maybe skip that step just to make it a little less tedious. Okay. And so I'm sorry, let me just go back. So basically, as we go back to the original function, notice the limit ends up 3 and 5, 3 over 5. And we talk about this in like pre-calculus. When you see a rational function with the same degree, top and bottom, the rule is you just look at the ratio of leading coefficients. Maybe you've heard that before. Okay, I certainly say it in my pre-calculus class. When the degrees are the same, you just look at the ratio of leading coefficients. And there's where your horizontal asymptote is, right? So we didn't use the word limit in pre-calc, but what we're seeing is a limit at infinity is a horizontal asymptote. Okay, and now let's look at this. Now, what we're seeing here, again, the highest power of the denominator is x, and so we're going to divide everything by x. So here's that first step where we divide. And then, notice what's happening here. That x, this x right here in the denominator of the numerator, what we're doing is we're just throwing it under the radical, and it's becoming x squared because, right here, square root of x squared is x. So we've changed the x to the square root of x squared because it's in the radical, and so it can cancel out with the other x squared in the radical, right? And just leave 2. Okay, so when x is positive, notice that's for when x is positive. Everything is okay. When x is positive, it's okay to do that, to make that substitution. And then denominator is pretty straightforward. Then we take the limits, a lot of little limits, we put it inside the radical, and then finally we take that limit, and of course, once again, all those guys go to 0. And we're just left with this, basically the radical 2 and the 3 is really the only thing that are going to be left. So there it is, radical 2 over 3. And once again, we kind of looked at that initial problem and seen those coefficients. And then something else, it says, as we compute the limit as x goes to negative infinity, we have to remember the square root of x squared is not x. Let me just give you a simple example. When x is negative 3, what happens when I square negative 3? Of course, I get 9, right? Positive 9. And then when I take the square root of the positive, the number I just squared, I get positive 3. So by squaring it and then taking the square root, the negative sign goes away, right? And that's why you see absolute value signs here. That's what happens to any negative number. And so 3, in relation to the original number, okay, 3 is not x, it's the opposite of x. That's what they're saying. 3 is, it's not negative x, it's the opposite of x. I changed the sign of x, basically, by doing that, squaring it when x is negative. Only when x is negative. All right, so when we divide, so that's why we just pull out a little negative sign there, and the whole thing becomes negative. It's because of that process. That we took a negative number, we squared it, we took the square root, we ended up with the opposite of the negative number. So that's only when x is going to negative infinity. And so the whole thing's going to play out the same way. You're going to get limits that go to 0, but as x goes to negative infinity, you'll have that negative limit. So and then finally, they're focusing on the vertical asymptote because you have the 0 value in the denominator, which is 5/3. So you have this other asymptote here. So we put it all together. We look at the graph. There's 3 asymptotes happening here. Okay, there's a horizontal asymptote at, this is the positive radical 2 over 3. There's another horizontal asymptote as x goes to negative infinity. And finally, a vertical asymptote at 5 over 3. Okay, so, and finally, this is the last thing from this section, limits at infinity. As x gets big, sometimes the whole function gets big, okay? So you could have it going big, it could get big in either direction, positive or negative infinity, as x goes in either direction. Here's an example for x cubed, right? Positive x cubed would get even bigger, positive, right? So it'd go to positive infinity. But negative, put a big negative number in there, cube it, it'll become a larger negative number. So you can see on the graph, both x is going forever and y is going forever, positive. But here, x is going forever in the negative direction, and so is y. So there's 2 different limits, as you're going out. But the limits are at infinity. All right, so that's all for this section. And I'm going to, whoops.